All right, so we're looking at the sodium flame test. I lost my microphone here. And you have you done this? You know, is it hot down here? Not really. You know, at the cone, on the surface of the cone, is where it's going to be the hottest, and right at the tip of the cone, it'll be the hottest. Up, you know, it's going to be the most stoichiometric. So here, just right there, you know, here it's not so hot. There's a lot of unburnt gas. You can see that. And so what we need to do is we need to do this. But you know, this platinum wire, I'm not sure if they cleaned it properly. And it always, you know, I'm going to just check the color of the flame here. Do you see the color?
Yellow.
Yellow. You know what that is?
No.
Sodium. Calcium's red. You might see other colors because people do flame tests for a lot of different things. We can't be so sure who cleaned this and who's testing what. And so in case there's lead, you want leads, do you want to be breathing lead atoms that have been vaporized in the gas, or silver, or mercury? No, you don't want to do that. And so what you're going to do is you're going to do this in the hood. And so it's hard to get a decent flame in the hood because, you know, the airflow. But still, you know, small flame with a nice cone is better than a big flame. You know, that's really structureless. And then you just put it right at the tip there. It's vaporized. And so what you have to do is you have to clean the platinum wire off so it gives no color or imparts no color to the flame. And the way we clean that is this. We use concentrated HCl and DI. And so you'll get a series of test tubes. And one test tube is concentrated. And so you dip it in the concentrated HCl, right? When you dip it, don't dip the glass part here. The glass is susceptible. If you get ions or whatever else in there, it'll devitrify. Have you ever heard of devitrify? In other words, it'll crystallize. And when it crystallizes, it's going to crack. Devitrify. Vitri is for glass. And so just... And so what you need to do is you dip it in the HCl and then you burn it. Dip it in the HCl, burn it. And then you have the DI for rinse. You know, you need to rinse. And so a lot of people dip HCl, rinse, and burn it. But I'd just dip HCl and burn it. I would do this, don't do this out in the open here because concentrated HCl, you don't want to breathe that stuff either. It's going to cause you damage to your mucous membranes, right? And so do all the flame tests inside the hood. And so what you're going to do is you're going to get a sample. Do you use your entire sample for the sodium test? No, if you pour it all in, you're going to waste all of it. We have to do all of our tests on just one sample. And so the sodium test is so sensitive, you just need a few drops to test for sodium. And so just get a couple of drops, put in the test tube or on a spot plate. You know the spot plates? Just put a couple of drops in there and then test it with a flame test. And so sodium is one of the easiest tests out there because it's so sensitive. But then it's one of the hardest tests out there because it's too sensitive. It's one of the hardest tests out there because it's too sensitive because everything gets contaminated with sodium. And even, you know, if you're doing, did I tell you this? When I was working with sodium chemistry, and we didn't want any sodium ions at all, because we were trying to put sodium ions into polymers. And but anyway, couldn't use Pyrex glass because Pyrex glass would leach out too many sodium ions. So how to use polyethylene, which didn't have any sodium ions. Well, our test isn't that sensitive, so you can use Pyrex test tubes, no problem. Go ahead and use those. But everything you touch will leave a sodium residue on it. And so if you got this wire nice and clean and then you were to touch it, then it's going to be heavily contaminated again, sodium. And so what you need to do here is watch out because lots of people get false positives for sodium. And so I'll tell you, the sodium in your unknowns present at such a high level is going to give you a very intense color. You know? If you're getting a very faint color, maybe you got some contamination there. And so what's involved in the flame test? We're going to show this by equations and observations. And so the way we show it by an observation is like this. The observation that's going to go with the flame test is we take our unknown aqueous and we put it into the flame. And then we get a yellow flame. That would be our positive test for sodium. All right, that's our observation. And then we would write an equation that goes along with this observation. And the equation is going to look like this. The equation is, we know our unknown must contain sodium ions. So we got sodium ions in solution. Then when we expose it to the flame, what happens is that the sodium ions get vaporized into the gaseous state. And so they're no longer in the aqueous state, but they're now in the gaseous state. In the flame, there are different parts of the flame. Have you ever heard of like the reducing or the oxidation parts of a flame? For example, where it's methane rich. Methane rich is in the middle, inside the cone. Inside the cone is methane rich, it's fuel rich. It's a reducing region. And then there's oxidizing regions. The flame is not totally homogeneous. And so some parts of the flame are more oxidizing environment, some parts of the flame are more of a reducing environment. In the reducing environment of the flame, there are electrons, and the sodium ions can get reduced to sodium metal. But these are sodium metal atoms in the gaseous state. And then there are collisions, because in a flame, a flame is a plasma, we call it. A plasma is a high energy gas, so the collisions, those collisions will excite the sodium's electron, one of the electrons, to a higher energy state. And so an electron gets promoted up to the, sodium's valence electron is in the 3s, right? And so an electron gets promoted into a higher energy orbital, and then it drops down. When it drops back down, then it emits yellow light. It emits a photon. And so we drop back down in energy plus h nu. H nu stands for photon. And it's going to be yellow. So there are other ways to excite sodium. We have sodium street lamps. You can see the yellow-orange color off the sodium street lamps. It's the same thing. They're getting it very hot. They vaporize the sodium metal to sodium gas, excite those, and then look at this. All right, each of you will check out a platinum wire, and you're going to keep it for the whole semester. I didn't know you were going to keep it for the whole semester. Therefore, if you keep it for the whole semester, you could start off with a sodium test if you want. You don't have to. You can go right on to the next ion. The next ion is...
that would be H4.
Yeah, we're going to do ammonium next. And the ammonium test, what's involved with that? Well, do we need our entire unknown sample? No. How much sample do you need?
They're claiming 10 drops, not just enough to do it.
Yeah, 10 drops. Actually, this one you want to use 10 drops for, because we need it to generate enough ammonia gas to detect that. And so in this, the observations are going to be like this. We take our unknown aqueous. And if it contains ammonium, ammonium is a base. And so we add acid to this. Or ammonium, is it a base? It's an acid, sorry. Ammonium is an acid, so we're going to add a base to this. In fact, do you know what base we're going to add?
Oh, yeah, NaOH.
NaOH, exactly. And then when we add the NaOH, then what's going to happen is we get it looks like nothing's happened. And so we get something called a CCS maybe, or we might get precipitates. Because hydroxide is a good precipitating agent, right? And you know, our unknown might contain other cations that might actually precipitate out with the hydroxide. And then we heat this up. We heat it up, and then the gas that comes off turns red litmus blue. The way, I mean, how do we test the gas? You know, what we have is we have it in a little beaker like this. And so the gas that's generated is going to be here. This will be the gas. And whatever gas this is, we need to have it come into contact with litmus paper. And so what we do is this. We take a piece of red litmus and wet it. A piece of wet red litmus paper will stick to the bottom of a watch glass. And we just let the gas that's generated come into contact. Of course, if the solution splashed on the red litmus, then it would turn blue because the solution contains sodium hydroxide. We're adding excess sodium hydroxide. And so we just want the gas to slowly, and it'll gradually turn blue. And it'll be very uniform in appearance, not spotty. And so the gas turns, well, if the gas turns red litmus blue, then the gas must be basic or acidic. The gas must be basic. Bases turn litmus blue, right? And so how many gases are there that are basic? Is oxygen basic? Hydrogen chloride? What's basic? That's a gas. Ammonia. And so the equation, we can see what's happening in the equation. If we have ammonium ions present and we add hydroxide, we're going to get ammonia. But ammonia is very soluble. And so most of this will be AQ. A little bit will be gas. You could write NH3 gas as well, and water. Let's say AQ and gas. You'll be able to smell it probably. But you know, we want to get more. We want a lot of ammonia gas. So to get a lot of ammonia gas, what we do is we just heat this. Right? Ramp up the temperature to generate NH3 gas. And so we'll get it all in the gas phase, or as much as we can in the gas phase. And so we just gently heat this. You know, we don't want any splattering. And we look for a uniform transformation from red to blue. If we see this, then we have a positive test for ammonium ion. And so this is just with 10 drops of unknown. That's going to leave the bulk of your unknown for the remaining tests, and that's what we need. How many drops or how many milliliters do you need for the remaining of this? How many? 10 drops? 10 drops for every other test? For this, okay, we're going to start off with the silver ion test. Does it really say 10 drops for silver ion?
10 drops of unknown.
Yes.
And the 5 drops of DI water. And 2 drops of 6 MSCM.
Yeah, pretty much.
A lot of them are 10 drops of DI water.
Okay, what it says 10 drops of unknown? Original unknown solution, 10 drops. Yeah. 10 drops is not that much, really. 10 drops is about half a milliliter.
5 times 10 is 0.5.
I would go 15 drops. Yeah. I'd go 15 drops, and then we'll make adjustments as we go along. I would, do you want to add, what does it say? 10 drops of original unknown plus how many drops of water? 5. What a ridiculous thing to do for me. To add 5 drops of water for what? For what purpose? To decrease the concentration to make your life more difficult?
You're supposed to add the washings.
What washings? We haven't even done any washings
I
yet.
think that's what the 5 drops of water is supposed to be. Yeah, you drop it and then you like.
No, I'm saying we're starting at the step 1 of the silver. What do we do at step 1 of the silver?
It does ask for 10 drops of unknown and 5 drops of DI water.
Okay, 10 drops of unknown and 5 drops of DI water. The DI water is to do what?
Let's find out. And then the next step is.
Well, if you got a solid in there, so I wouldn't. I'd just do 15 drops of unknown. All right, and so this is where we totally deviate. You know, the 2 drops is a guideline, so you write that in your notebook. But you know, what you do in the procedure may be, 100% different than what's in the written procedure. And so what we're going to do is we're going to adjust the amounts as we go along. And so I say use 15 drops of unknown. You know, the more unknown, then hopefully by the end of the 60th step, we still have something left, to test. Because each step you lose something, a little bit of something, a little bit of that. And so, well, how do you set up the notebook for this? The way I set up my notebook is something like this. I'd have the unknown. This would be a flow chart. And I think they use this. Do they use dash boxes and solid boxes? What do the dash boxes represent? They don't have dash boxes and solid boxes?
Yeah, both of them are all solid.
They're all solids. All right, I was thinking of dashing and, that's okay, I don't need to see it. And making dash boxes and solid boxes indicate a solution versus a solid, just to keep it. Or you could use different colors or something like that to keep track. Or, you don't need anything.
They mark it as the precipitate on the left side.
All right, that's fine. All right. So we have our unknown aqueous. And then how many drops of silver nitrate? 2 drops?
You mean of HCl?
Of the HCl, sorry.
They asked for 2, but you might want more for the full precipitation.
Yeah. 2 drops of HCl, and then what we're supposed to get is a precipitate, right? AgCl is our precipitate here. That's what we're supposed to get. But 2 drops might be too much or might not be enough. For example, if we have no silver ion present, then the first drop is not going to do anything. And then we could add a second drop just to make sure that we don't, right? And then we might stop there. We'll probably stop there if we're not getting any precipitate.
If it does precipitate, would you put more than 2 drops in that case?
Yes.
Okay.
If it does precipitate, I would put more than 2 drops. I'd keep adding until what?
Then you don't see it spark.
Right. What you want to do is you want to keep adding. You keep adding until you maximize the amount of precipitate. You have to be very careful because sometimes if you keep adding, the precipitate starts to disappear. You don't want that to happen. And so you keep adding until you can't see any more cloudiness develop, and then stop there. Sometimes it's very hard because if you get a cloudy white solution, it looks like milk or something, and you add a drop, you can't see anything happen, right? Yeah, but what we'll do in that circumstance is we're going to centrifuge the test tube. We have centrifuges. Actually, we're running low on centrifuges. How many centrifuges we have?
3, 4, maybe over there.
10 milliliter beaker. Not 10 milliliter beaker, 10 milliliter graduated cylinder. Somebody left. Those 10 milliliter grad cylinders are expensive. Somebody left theirs in the hood. How much are those? No.
Oh, that's the list you should
$24 worth of grad cylinder is in the hood.
figure out what not to do.
It's like somebody leaving $24 out of their wallet in the hood.
Just hang on to sell it back to half price.
Yeah, actually, that's. I wish I could do that. I think I'd get fired.
Collecting our students.
Yeah. Otherwise, I'd go through everyone's drawer and pilfer it. Take everything. All right. We have different size test tubes, right? And so these centrifuges will have different size of these holders. And so you got to make sure it doesn't sink to the bottom. Well, if it sinks to the bottom, just pull out the whole thing. But some of these will have liners so that you can use smaller test tubes like this. The medium ones fits in here. There's some with really tight liners for the baby-sized test tubes here. So when you do centrifuge, we have to counterbalance, right? Otherwise, it'll start to rock. And I can't believe I don't have any test tubes here. Oh, here. Put them all down here. All right, I found 2 test tubes. And so we just counterbalance with a little water, whatever the height is.
How exact do you have to be? Like within a
Not that
centimeter or
exact.
so, or-
Yeah, hopefully closer than that.
Okay.
Centimeters too. Let's say these are pretty close, within a couple of millimeters. It's fine. So we put those in here
Opposite sides.
on opposite sides. This one has an insert for a little one. Let's try this one. The blue ones are for the baby. All right, and then just flip it on. There's a little timer switch here. So we flip this on. And then we let it get to maximum RPM. You can just hear it. No, you just bring it to max and then shut it off. Once it hits max RPM, then shut it off. And then it takes a long time for it to come to a stop, so we'll break it. The way we break it is just use a paper towel or something. Don't break it to a sudden stop. What you want to do is you just want to break it to a gentle stop. If you go to a sudden stop, the precipitate will, and then that should be it. So that's what it looks like when it's properly balanced. Let's not counterbalance this one. Let's just try this one with a test tube like this and see what happens here.
Looks like my washing machine.
Yeah. Alright, we don't want to do that. Sounds bad. Alright. It didn't make it to full speed. There. And it's probably going to rock off the bench here. So the centrifuge is a rapid way to compact the precipitate. And so if I had 2 drops and it's too cloudy, I can't see anything, just centrifuge it. Doesn't take very long. And then the precipitate will be packed at the bottom, giving you a clear solution. And so you could just, you could add a drop and see instantly if you get more precipitate or not. What we want to do is we want to make sure we get all the precipitate out that we can. That is, we want to precipitate out all the silver. Because if we don't precipitate out all the silver, then what happens is, if we didn't get all the silver out of this, then we have the decantate, or what's another name for the decantate? Supernatant. If the supernatant contains silver ions, then it screws up all your subsequent tests. Right?
Silver chromate, nuh-uh.
Yeah, your colors are going to come out bizarre. You're going to be coming up to me, saying, I don't know what's going on here. You don't know what's going on because, you got contamination. interfering ions, like silver ions. And so this 2 drops is just, ignore that. Use it as a guide, but we gotta, if it takes 10 drops, then so be it. It takes 10 drops to get all of it out, right? However many drops it takes, use that. Otherwise, you're not going to have success for the rest of the experiment. Does that make sense? Likewise, how do I separate the precipitate from the decantate? So we have the other ions here. Well, there are 2 ways to separate the precipitate. Do you guys have these?
Yes. Yeah.
These come in handy. One way we could do that is we suck the solution off the top and then transfer it to another test tube. Another way is we pour it. This is called decanting. Just pour it off. But when we pour it off, do we get all the solution off there? No, so we might try to suck the top of it, but we don't want to get any precipitate into our decantate, right? In the end, you aren't going to be able to get all the decantate off there. There's a problem with that too, because if the other ions contaminate our silver chloride, then that screws up the subsequent tests here as well. And so what we have to do is we have to wash off the precipitate because it's contaminated with decantate. And so the way we wash it is we just add some water and then get a stir rod and then mix it up, centrifuge, and then what should we do with the rinse? Should we discard the rinse? Kelly, this was your question yesterday. We don't discard the rinse because that rinse contains ions. The more ions we lose, the harder time you're going to have over here. You don't know how many people end up here and they get nothing. They're doing the test and they get nothing. And everything's disappeared. They're already 2 days into it. And they're thinking, oh my God, well, they lost it all. Well, anyway, so what we need to do is we need to get those ions, in the decantate back into our decantate solution. And so this is why it says pour the washings in with your decantate, because we don't want to lose the ions, right? How many washes should we do? Well, as many as it takes is very difficult. How do you know when your silver chloride's been washed off thoroughly? You wash it not just once, but you wash it, how many times does it say? 3 times, right? It says to wash them 3 times. And so the first wash, you pour the rinse in with the decantate. The second wash, do you pour the rinse in with the decantate, or do you discard the rinse? What does it say? Add all 3 washings to the decantate, or add all 3 washings to the decantate? It says that.
It says washings go up.
Well, tell me what it says. How to wash it.
Wash the precipitate with 10 drops of distilled water, centrifuge, and add the washings to the decantate.
Okay, so then are we going to do a second washing, or that's it?
And then you're just going to dissolve the precipitate with 4 drops of 6 and then add the 6 nitric acid until it's acidic liquids.
All right. If it says to wash with 10 drops, what I would probably do is this. Even though this is going to be a bit more of a hassle, I would either do a 5-drop washing. Well, 5 drops might not be enough, but I would probably do a 5-drop washing, add that there. Do another 5-drop washing, add that, and then do another 5-drop washing and discard it. All right. The reason is by the third washing, it's probably nothing or minimal, and it's probably not worth diluting your decantate. You see that? The problem is if you do one 10-drop washing, then your crystals are still going to be contaminated on the surface. So you want to do it in a sequence of washes to more thoroughly wash it off. Okay, with each washing, again, we wash, you get a stir rod, mix it up, and then put it in the centrifuge and do that. So, No, we don't do that. We're going to assume that, yeah, the way we know that there shouldn't be any silver ions left is we make sure we so that, you remember when you're doing the barium chloride to the sulfate unknown in Chem 1A? There, you always add a drop to make sure no more precipitate forms. The same thing here, you're going to add a drop to make sure no more precipitate forms. And we'll be okay. You don't want to add too much HCl here, because if you add too much HCl, in the next step, we've got to add base. And so if you have a ton of excess HCl here, then you're going to have to add a ton of base to neutralize that, and pretty soon you're going to be transferring your test tube into a beaker, right? Which always happens. All right. What's the next step? Well, the next step is we're going to do a confirmation test of our precipitate. Actually, you know, with HCl, 3 things can precipitate here. We could get silver chloride, lead chloride, or mercury chloride. You know, lead 2 chloride, mercury 1 chloride. And so this isn't positive yet for silver chloride because there could be some PbCl2 and or Hg2Cl2. For ours, there isn't any because they tell you there isn't any, but for general unknown, we don't know. And so what we have to do is we have to test the precipitate chemical properties by adding Are we adding no, we aren't adding nitric. We should be adding ammonia. We add excess ammonia. Here. Don't add too much. What are you supposed to do with this ammonia? Actually, you know, we don't really want to add excess. We want to add just the right amount of ammonia. And so how can I tell what is the right amount? How many drops do they say? And 4 drops, but you know, that might be too much or it might be too little. So what are we trying to do in this particular step? We're trying to dissolve the precipitate. Your precipitate is only silver chloride. You don't have any lead or mercury in there because it's a simplified version of this test. But what we're going to do is we're going to add just enough to dissolve it. It could be 1 drop. If you add 1 drop of ammonia and it dissolves, should you add the remaining 3? No, because it's going to screw up your subsequent step if you add too much ammonia, right? If you add 4 drops and the precipitate's still there and hasn't dissolved and you're crushing it with this stir rod and it's still not dissolving, what should you do? Add more. Add more until it's all gone. And this requires some stirring with the stir rod because you want to break it up, you know, to make sure it's dissolving. And so we add just the right amount of ammonia to do what we want. And what we want to do is we want to dissolve that precipitate. When the precipitate dissolves, we form this complex. It's going to be the diamine silver ion plus the chloride. And so it goes into solution. Mercury and lead will not form those complexes, so we don't have to worry because when we add excess ammonia to lead, nothing happens, lead chloride, and when we add excess ammonia to mercury 1 chloride, nothing happens. Just the silver chloride reacts, and so this is very specific to silver chloride, this reaction compared to the other. All right, and then what we're going to do now is we're going to add nitric. And again, I don't pay attention to the amount that's written in the procedure. I pay attention to what I'm trying to do. What am I trying to do here? I'm trying to regenerate the precipitate. I regenerate the precipitate by this. The nitric acid will attack the ammonia and reprecipitate out the silver chloride solid. Now this, if we get this sequence, we get a positive test for silver ions in our original unknown. And so let's take a look at the observations and the equations that we have for silver. And in this case, I'm going to break it up into steps because we have multiple steps. And so the first observation, which we'll call 1, this is for the silver test, is that we take our unknown AQ, and then we're going to add HCl to this, and we get a white PPT. And the equation that's associated with this is just silver ion will precipitate out with the chloride ions in HCl to form AgCl solid. All right, then in the next step, we dissolve that. And so the observation would look like this. We take our white PPT from step 1, so I'll label it white PPT 1. And then we're going to add the ammonia to this, and then we should get a CCS. The CCS stands for clear colorless solution. The equation for this will look like this. We have AgCl plus solid plus 2 ammonia is going to yield AgNH3 2 plus a chloride, AQ. This is a Lewis acid-base reaction. This reaction we're going to look at in much more detail in chapter 18. And so for right now, we'll just leave it like this. Then in step 3, we regenerate this. And so we take the CCS from step 2, and then we add, the nitric acid to this. And add the nitric acid, we generate the white PPT. So we'll just say white PPT here. There are 2 ways I can show what's happening here. I'm going to show this via Le Chatelier's principle. We haven't talked about yet. But you know what Le Chatelier's, have you heard of Le Chatelier's principle? Le Chatelier's principle works like this. So this would be the observation. The equation for something like this, we're going to try to visualize as a 2-way reaction. And so, there's reaction going forward, reaction going backwards, which side's favored? In this case, when we have excess ammonia, generating the complex is favored. And so we have a CCS. But when we add the nitric acid will attack what in this? This is an equilibrium, all chemical reactions are. It'll attack the ammonia. And so when we add the nitric acid here, the H plus in nitric acid attacks ammonia to form ammonium. This is a very favorable reaction because we have strong acid, nitric acid. Yeah, that'll attack the ammonia here. Okay, when the ammonia is attacked like this, let's say, in this case, we'll have, let's say, 2 H plus to generate 2 ammoniums. Then what that does is it removes the ammonia from here. If it removes the ammonia, what this is going to do is it's going to shift the reaction backwards. It shifts backwards. So we remove reactant, the reaction shifts backwards. This is what we call Le Chatelier's principle. The way it works is like this. If we have our water well, like this, and we call one side the reactants, the other side the product. If we start removing water, from the reactant side, what's going to happen? Well, the water is going to flow backwards to make up for that. And so the same thing happens here. If we got some kind of equilibrium situation and we start removing the reactant, it should shift to form more reactant to re-equilibrate things. Le Chatelier's principle. Le Chatelier's principle, yeah. All right, so this is a Le Chatelier's visualization of the reaction. Or we could just write it, you know, as the reaction like this. If we write the complex plus chloride plus nitric acid, the H plus in nitric acid. Nitrate's a spectator in this particular reaction. Will attack the ammonia on the silver, freeing up that and allowing precipitation to occur. This is occurring in multiple steps here, but we'll just write in one step. All right, so this is the test for the silver. What comes after silver?
Three metals, the three pluses. Iron, aluminum, chromium.
Okay, iron, aluminum, chromium 3,
Chromium.
or chromate?
Chromium 3, I'm sorry.
Iron, aluminum, and chromium 3. All right, so we go back to our decantate. Hopefully you didn't throw it away. And it's still there. In fact, in this lab, don't ever throw anything away, whether it's a precipitate or a decantate, unless you're absolutely certain you don't need it. Because sometimes they say, okay, put away the decantate, and then 2 pages later they ask for it back. You know? Or sometimes, you know, the precipitate, they don't mention it, and then 2 pages later, that's back too. And so don't throw anything away prematurely. And so here we have the decantate 1, we'll call it. And then we're going to add what to the decantate 1? The decantate 1 is going to contain iron 3, aluminum 3, and chromium 3, plus other ions, right? There's going to be other ions in there. Well, what do these have in common? All these are 3+ ions. 3+ ions are highly soluble or highly insoluble? 3+ ions are highly insoluble, usually. They aren't very soluble. And so what are we going to add to this to separate it from the others? So we want to separate these 3 ions from all the others. What do we add? NH3. We're going to add ammonia. We're going to make it basic. Just slightly basic. Just slightly basic. Because these don't need much hydroxide, we're going to precipitate these 3 as hydroxides. We have different levels of hydroxide precipitating agents. Sodium hydroxide is one of the most powerful because that leads to a high concentration of hydroxide. And so if you use, let's say, 1 molar sodium hydroxide, you're going to get 1 molar hydroxide to precipitate. But let's say we use 1 molar ammonia. If we use 1 molar ammonia, are we going to get 1 molar hydroxide from that? No, we're going to get a very small amount of hydroxide. And that's all we want, because there are other ions in here that would precipitate out with a high concentration of hydroxide, such as magnesium. Magnesium's present in here, so if we add too much ammonia, or if we add too much hydroxide, then we're going to get iron, aluminum, chromium, and magnesium. Do we want magnesium to? No, because if magnesium gets stuck over here, then we're never going to detect it over here. Plus, it's going to screw up all our tests. And so we have to be very careful about the pH here, because too high of a pH means we have too much hydroxide. And so we got to get the pH, you know, just to neutral. Actually, you know, oddly enough, these guys will precipitate out in acidic solution. Can you believe that? In acid, is there hydroxide in acid? it turns out there is hydroxide in acid. Where does the hydroxide come from in acid? From water. And so these can precipitate out with a minuscule amount of hydroxide. So be careful. Don't add too much ammonia. If you add too much ammonia here, you're going to get some magnesium and whatever else mixed. And you don't want that. And so what we're going to do is we're going to be very careful. Well, this solution should be acidic because we just added a bunch of HCl, right? And so this should be highly acidic. So we got to make it just neutral. And how do we test that? With litmus. Do you dip the litmus paper inside? No. No. What you do is you dip a stir rod, right, into the solution and then put a drop of solution on the litmus. That's how you test it. And so we're going to carefully add our ammonia until neutral / basic. You don't want to go too basic, otherwise you're going to have trouble. If we get the hydroxide just right, then only 3 ions should precipitate out. Yeah, and so remember what I said about maximizing the precipitate? In this case, this is going to be maximizing. By the time you hit neutral pH or slightly basic, all of it should be out because these things are really insoluble. Okay. This is something you'll learn in chapter 18. We haven't really gotten there yet. Learn this. And so if we have all 3 of these, we're going to get iron 3 hydroxide. Do you know what color that is?
Red.
No. Rust colored.
Oh, brown.
Brown, right. Red-brown. Aluminum hydroxide. Do you know what color that is? It's white or colorless. Chromium hydroxide.
That one should be colored.
Well, what does it say in the book? What color is it in the book?
Gray-green.
Gray-green.
Yeah.
Right? Gray-green. So you get a mix of these precipitates. Okay, in the decantate, hopefully we have all the other stuff we don't want. All right, so it's the same drill here. We want to wash our crystals off, right? And so we follow the same standard washing procedure. We don't do it in one step. We try to break it up into 2 steps or maybe 3 steps, right? Uh-huh. Question?
It says also add 2 drops of chloride.
Okay. You know what? Ammonia is a base. Ammonium chloride is a acid. You need to add the 2 drops of ammonium. Why? Because that's what we call a buffer solution. Ammonia / ammonium, you know, normally when you mix an acid with a base, they neutralize each other. But these are both weak, and so when you mix an acid and a base, in this case, they don't neutralize each other. And so we have a solution that contains both acid and base. It's like amino acids. Have you all know amino acids, right? Amino acids are a base on one side and a acid on the other. And so they're both an acid and base. And so they're kind of weird because usually when we think about amphoteric materials, we think about the same species, but in that case, you know, you have a base on one end and an acid on the other. Well, this is one molecule is an acid, the other molecule is a base, and this is what we call a buffer. And buffers help maintain a more stable pH. Like I said, the pH is critical here because if we get too high of a pH, then we start precipitating other ions. The +2 ions will start to precipitate. If you get the +2 ions precipitating, then you're in trouble. Right? We can't have the +2 ions precipitating with our +3. We only want the +3. And so the ammonium is just a safeguard to make sure you didn't get the pH too high. Okay. Uh-huh.
If you get the pH too high, you just lower.
Yeah, well, if you overshoot with too much ammonia, then you just add a little bit of acid. You add a drop of HCl or add a drop of nitric. Usually in metathesis, we want to use nitric. In redox, you know, HCl, that kind of thing as an acid, just an acid source. You know. So in this case, we probably use the HCl because we just added some HCl just to bring the pH back down if your pH gets too high. You don't want it to get too high. That is, if the litmus turns dark blue, then you're too high. All right, where do we go from here? So we wash it, you know, as we always do, and then add at least the first, maybe the second washing to the decantate, not the third wash. Do a third wash. And then with these crystals, what are we going to do? The precipitate. After the washing, we're going to so now we got a mix of a rest red and a white colorless and a gray-green precipitate. So you might be able to tell. You might not be able to tell. These colors might be hard to detect. So what we're going to do is we're going to separate the precipitates using the chemical properties of these precipitates. And so what are we going to add to the precipitates next? Sodium hydroxide. Well, didn't we just try to avoid adding too much hydroxide, and now we're going to dump in sodium hydroxide? Why is it safe to do now? Because the +2 should be safe. You know, the +2 should be separate now, away from this. And so adding sodium hydroxide here is not going to be any problem at all. When we add the sodium hydroxide, what happens? What does the sodium hydroxide react with? Does it react with the iron 3 hydroxide, aluminum hydroxide, or the chromium 3 hydroxide? It reacts with the, just look at the flow chart. Are you looking at the flow chart with me? It reacts with the iron.
Aluminum.
It reacts with aluminum. Right. It reacts with aluminum because the aluminum does something funny. Aluminum, when we add too much hydroxide, forms a complex. What's the name of this complex? Here. This is called tetrahydroxo aluminate ion. Well, doesn't iron, can we form tetrahydroxoferrate and tetrahydroxochromate too? You know, do we form tetrahydroxoferrate? Look at the flow chart and tell me, do we form tetrahydroxoferrate?
No.
No. How about tetrahydroxochromate? 3. Forgot the Roman numeral. No. And so the big question comes, why not? This is a Lewis acid-base reaction. Hydroxide's a Lewis base. Why not? Why don't we form tetrahydroxoferrate 3 and tetrahydroxochromate 3?
Wait, but aren't the coordinate numbers the same?
Coordination numbers are the same. So the question is, why not? Hydroxide is a good base. So what did I say about predicting Lewis acid-base reactions? Somebody remind me. About predicting Lewis acid-base reactions. What do you need to know? If it's favorable, it should react, yes. No, Lewis acid base is no oxidizer, no reducer. Kelly?
Is it a good Lewis acid?
What's your definition of a good Lewis base and a good Lewis acid?
The good Lewis acid would it would
Is there a chart? Why is there no chart that just ranks the Lewis acids and Lewis bases? Like Bronsted. Why is there no chart that ranks the Lewis acids and Lewis bases like Bronsted? Bronsted is so easy to predict.
Because of that is what it's mixed with. Like the other species around or something like that?
Yeah, something like that. So be more specific. That's not a good answer for a test. Can't what? Well, electron pair donating ability is what you can. I mean, electron pair donating ability depends on what? Because what happens when an electron pair is donated? It forms a coordinate covalent bond. Do you guys know the theory well enough? The bonding theory? What is the bonding theory that we use to describe coordinate covalent bonds? Molecular orbital theory. And so we need to see, you know, remember, I don't know how long ago this was, but this was what, first week of class we were talking about this? It's not the valent, it's how, in other words, you need to know LCAO. Somebody remind me what LCAO is. Linear combination of atomic orbitals. And when we're looking at linear combination of atomic orbitals, it's going to depend on the quantum mechanics that the particular. And so it's not the simple thing because versus Bronsted. Bronsted is a very simple thing because we're just forming same type of. I mean, the acid's always the same, so the only thing is the base. Well, anyway, so the answer is why? You would say, I don't know why. It just is that way. It must have to do with the bond formation, right? It must have to do with the quantum mechanics. And so what we know, you know, as far as why does, you know, excess hydroxide do this to aluminum but won't do it to iron 3 and chromium 3, you have to look at it in much more detail. In other words, we can't just have a simple thing. This is a stronger acid, this is a stronger base. That doesn't work here. We have to look at it in much more detail. In fact, we have to go into the quantum mechanics of the bond. And so for us, what does that mean? For us, what that means is we just look it up in a table. In Appendix D, we see what commonly happens when we mix ligands with essential metals. And so we don't actually predict it, we just observe what happens. You should be able to predict it using theory. But anyway, the other two don't do anything, right? And so the iron, I don't know if I have this written, I didn't have my lab manual in the same way, but the iron 3 hydroxide stays as a precipitate, as does the chromium 3 hydroxide. These are solids. This is aqueous here. All right, then what are you doing? You're adding hydrogen peroxide to what? The precipitate or the solution? The precipitate. Now, what is hydrogen peroxide? Normally when you think about hydrogen peroxide, you think what? Acid? Base? Precipitating agent? Oxidizer? Reducer? What do you normally think about hydrogen peroxide? Oxidizer. And so typically hydrogen peroxide is used as an oxidizer. What do you think we're going to oxidize here? Can we oxidize iron? Like say maybe iron 3 to iron 4? No. Can we oxidize chromium? Yes. You can oxidize chromium. Because chromium is +3. What is chromium's max ox? Chromium's max oxidation state is +6. And so let's do this. When we oxidize chromium, we're going to form what? Was this a combined step? Are you adding the sodium hydroxide and the hydrogen peroxide at the same time, or doing it separate?
Well, actually, in the lab manual, it goes aluminum first. Well, they're just showing you that they're kind of simultaneous, but aluminum first, and then iron, and then
Chromate.
iron first, aluminum, and then chromium.
All right. Chromium is what?
You're adding
Yeah, you are adding
to the different state.
All right. What's the hydrogen peroxide going to attack here as an oxidizer? It'll attack the chromium. When hydrogen peroxide attacks chromium, what forms?
CrO4. Minus.
Cr2O7 2 minus or CrO4? Dichromate or chromate? Just take a look on the chart and see which one forms. Is it dichromate or is it chromate? Because did you know dichromate and chromate have the exact same oxidation state? Oddly enough, dichromate and chromate have the exact same oxidation state on chromium, which is +6. So when we oxidize chromium 3 to chromium 6, does it get oxidized to chromate or does it get oxidized to dichromate? Well, just look at your flow chart and see what results. Is it chromate or dichromate? It's chromate. That's important because do you know what color chromate is? It's a yellow solution. Do you know what color dichromate is? You should know. You better know what dichromate is because you just used it last week. What color is dichromate?
Orange.
Orange. And so this is important to know because if we form chromate, it's yellow. If we form dichromate, it's orange. And so we're going to form, well, then we should know because the gray-green precipitate should what? Disappear and be replaced by a yellow liquid solution, right? And so we got chromate over here. And the precipitate iron 3 is not oxidized, so iron 3 is just going to stay as iron 3 hydroxide solid. Are we good? But there's something very strange about chromate and dichromate. Chromate and dichromate depends on the pH. Which form we have. These are interconvertible forms. And so at high pH or low pH, that changes the form. And so if we, let's say we have chromate, 2 chromates. We can convert it to dichromate by adding acid. If we add 2 H pluses, do you know what forms? Dichromate and water. Dichromate and water. This is a reversible reaction here. And so we're going to use a little bit of the Le Chatelier's principle here. Le Chatelier's principle says this. Imagine this is 2 water wells here. If I add more water to this side, which way will the water flow? It's going to flow to the right. And so what I do is if I add more acid to this side, then I should convert chromate into dichromate. Likewise, if I remove acid from this side, it should shift this way and go to chromate. And so what we can do is we can interconvert the two forms by adding or removing acid this way. And so we can change the color of this easily by just adding acid or adding base. It's very easy. And so what are we going to do with the chromate here, the yellow chromate? Well, we got to separate it from the iron. So how do we separate? We got to wash it, right? Add the decantate, wash, and then throw away the rinse. We want this stuff to be clean, the iron 3, as well as this. And so once we have the, well, which one are we going to test first? The aluminum, the chromium, or the iron? The aluminum?
No, they asked for iron first.
They asked for the iron first? All right, let's test for the iron first. So what are we going to do to the iron? What time is it? I'll just talk about the iron and then we'll wrap it up. We're going to add what?
They're asking 10 drops of 3M NaOH.
Okay. What's that going to do? Then what?
And 5 drops of 3%
Oh, no, wait a minute. That's already over here. And in fact, these two steps were combined, sorry.
That's what I was saying.
Those two steps were combined. The sodium hydroxide was to attack the aluminum. The hydrogen peroxide was to attack the chromium. Okay, then go on, move forward from there. The sodium hydroxide, remember, the 10 drops is just a guideline. We want to add enough sodium hydroxide so we get rid of all the white PBT, all the aluminum. Oh. Yeah, skip ahead. All right. All right, so here we wash this. This should be clean, and then we could dissolve this in nitric acid, hydrochloric acid. So we dissolve this in hydrochloric acid, and so we just get iron 3.
Oh, and you're also supposed to add the iron complex, the potassium iron complex.
Yeah, okay. So we dissolve our precipitate, the iron 3 plus other stuff. And then we add, what's the complex?
It's the potassium hexacyanoferrate.
Okay, hexacyanoferrate what? 2? How many potassiums do we have?
4.
Yeah, then you're right. Potassium hexacyanoferrate. Isn't cyanide super toxic? Yeah, but cyanide is going to be complex with the iron, so we're safe. Not to worry. In fact, they use this potassium hexacyanoferrate to dye blue jeans.
Is that acid wash?
Well, anyway, when we do this, what are we going to form? Fe3 irons?
And no, Fe4.
4 irons?
Yeah, 4. And then the hexacyanoferrate.
So this would be iron 3 hexacyanoferrate 3, or 2. Hexacyanoferrate 2. This is a solid. What color is this?
Blue.
Blue. It's called Prussian blue. And gives a nice blue color. So this would be the positive test for iron. So let me just wrap it up with the observation. We would do the same for the chromium and aluminum, but let's just wrap it up for iron here. Okay, for the iron test, we're testing for iron 3, not iron 2. So the iron 3 test is going to look like this. We take our original unknown, AQ, and then we add the HCl, and then we get NR. The iron 3, nothing should happen with the HCl. The equation for this is iron 3 plus HCl yields Nr because no precipitate, no gas formation, no whatever. And so this is one observation and equation. All right, in the next step, then we added the ammonia, is that right? To the decantate. Yeah, to the decantate. And so we go solution 1, this is 1 relative to iron, plus ammonia yields, this should give us a kind of a red-brown PPT. And so if we have iron 3 plus and we add aqueous ammonia, we get 3 ammonias plus 3 waters. This should give us iron 3 hydroxide, solid plus 3 ammoniums. We got our precipitate. And then in the next step, we added excess sodium hydroxide to this. And so we take our precipitate from step 2 plus the NaOH. Actually, I did it arrows. I'm being inconsistent now, but it's all right. Plus the sodium hydroxide gives us Nr. And so we don't expect iron 3 hydroxide solid to react with the sodium hydroxide. Why? Because we're told this. You know, hydroxide is a good Lewis base, right? It's not going to attack it. All right, then eventually, well, we're going to take our precipitate from step 3. Nothing precipitated, it's just our solid, I could say, from step 3, and then add the hydrochloric acid, right? Then we get a solution. The solution, it might be very faint, you know, it might be red, yellow solution. The color might be too faint to see. And so here the reaction is the iron 3 hydroxide solid will be attacked by acid, you know, 3H plus. I'll just write it in anionic form. It's going to give us iron 3 plus 3 waters. This is a metathesis or Lewis acid-base reaction. Not Lewis, Bronsted. Step 5 is we take the solution from 4 and then add the potassium hexacyanoferrate 2, and we get a blue precipitate. And so the reaction here is we're taking 4, how many irons do we get? It's minus, yeah, we're taking 4 irons, so F4Fe3 plus 3 of these hexacyanoferrate ions, which have a 4 minus, yields Fe4, FeCN6, 3 solid. And so what we do is we follow iron 3 from the very beginning to the very end, you know, ignoring everything else. But we still have to see how it reacts, because the purpose of the HCl was to get rid of the silver. The purpose of the ammonia was to precipitate out the iron. The purpose of the sodium hydroxide was to get rid of the aluminum, etc. But we show what happens, you know, because it's being exposed to those. All right, I'm going to stop here and then let you get started. I think the original unknown solution should be available in the stockroom. Okay, you're going to each of you will check out a platinum wire, and then you can start. You could start with the sodium test. You could start with the ammonium test, or you could start with the silver. Right away.
Hey, do we have to start on sodium first?
You could work with a partner.
Should we weigh out our crystals?
You can weigh out your crystals anytime.